Hello, dear students. This is Shakil, and today we are going to discuss magnetic fields in A2 physics syllabus. And the topics that we will discuss today will be the force on charged particles inside magnetic field and the Hall probe. Hall probe is a device that is used to measure magnetic field strength. So let's look upon the syllabus content. This is our video lecture 2 about the magnetic fields. Well, firstly, we'll look upon the direction of force on moving charge. Then we will look for the quantitative analysis of that force. We'll derive this expression, and then we will look upon the Hall voltage. This is actually the Hall probe, and we will derive an expression. So in this video, we have to cover these first 3 points from this syllabus. The next 3 points in this syllabus topic will be covered in video lecture number 2. Okay, so let's look upon the topic, which is force on charged particle inside magnetic field. Well, we are already done with force on current carrying conductor inside magnetic field. So this is a bit of the similar topic to that. So the charged particle means proton, electron, a nucleus, alpha or beta particle, or it can be an ion. When the charges move, they generate a magnetic field around them. Like this is their natural intrinsic property, that when a charged particle moves, it changes its position, then it produces a magnetic field around it. Well, in the presence of another magnetic field, like if the charged particle is moving inside a magnetic field, and it is producing its own field as well. So there would be two fields. So these two fields will be interacting with each other. And due to this interaction, this can result in a magnetic force acting on the charged particle. So this is basically the reason, the interaction of the magnetic field by the charge and by the external field. Well, there can be three situations. Let's look upon them one by one. So first of all, first situation is the charge at rest inside the field. As you can see that the series of crosses are there that represent the uniform magnetic field pointing into the screen. Like these all crosses are part of uniform magnetic field that is pointing into the plane of the paper. Okay, then there are two charges shown inside that field. The one is the positive and one is the electron or negative, and they are at rest. Well, when they are at rest, so there would be no magnetic force acting on the static charges as they are at rest. So they are not having their own magnetic field. So no interaction between the fields. So hence no force will be acting on the charged particle. Well, about situation 2. Situation 2 is when the charged particle move parallel to the magnetic field. Like the charged particle is moving parallel to the magnetic field as it is shown in the diagram. You can see that there are two poles, north and the south one, and the magnetic field lines are moving from north to south, and the proton positive charge is moving from north to south, and electron is moving from north to south, and they are moving parallel. So when they move parallel, well, they will again experience no magnetic force. And why is that? Moving charge has its own magnetic field, okay? But if its movement is parallel to the magnetic field, it will not interact. Then the magnetic field of the charge will not interact with the other magnetic field lines. Hence, there would be no magnetic force. So situation 1, when the charge was at rest, no force. Situation 2, when the charge is moving parallel to the field, no force again. Okay, now look at the situation 3 now. Situation 3 is when the charged particle will be moving at some angle, and that angle will be from between 0 and 90 to the magnetic field. Well, it can be equal to 90. Okay, so what will happen then? Well, two diagrams are there. The first one is the crosses, which means the magnetic field is pointing into the plane of the screen. Electron is moving at right angle, entering at right angle to the field. Of course, it will experience a force. The other one, the proton moving at some angle to theta, some angle theta to these magnetic field lines. Of course, it will again experience a magnetic force. So the magnetic force will act on the charge moving at some angle with magnetic field, since the two fields are going to interact over there. Okay, now we have to look for the direction of magnetic force on moving charge inside the field. So again, we have to use Fleming's left-hand rule for that. The same rule as we applied for current carrying conductor, FBI. Over here, I will be Q by T, because this I or Q is actually the direction of the moving charge. So, well, you will point your first finger towards the magnetic field direction, and you will point your second finger towards the direction of motion of positive charge. And then the thumb will show the direction of force on the charge. Well, you have to note that the force on the charge will be perpendicular to its direction of motion. Well, this magnetic force will be perpendicular to direction of motion. As this will result in moving along a curved or circular track, because you know the perpendicular force changes the direction of object from linear to circular. Okay, now we have to look upon size of factors of the magnetic force on moving charges. So there are like same factors as we have studied in current carrying wire plays in magnetic field. Of course, the first factor is magnetic field strength itself, greater the magnetic field, greater the magnetic force. The second is the size of the charge. Bigger the charge, bigger would be the magnetic force. The third one is speed of charge. Faster the speed, greater would be the magnetic force. So we can arrange this in this equation where magnetic force is BQV sine theta. So where theta is the angle between B and V, like V is the direction of motion or velocity or speed. Okay, so maximum magnetic force happens when theta is 90, because sine 90 is 1. Minimum magnetic force is when theta is 0. It means when B and V are parallel. It means when charge is moving parallel to the field. We have seen that. And if the angle is between 0 and 90, of course, you have to use BQV sine theta. Okay, next thing is Hall probe. Well, this is the important topic. Hall probe is a device that is used to measure magnetic field strength or magnetic flux density anywhere inside a magnetic field. First, we have to look upon its shape and its construction, right? It is similar to like ammeter or voltmeter. Ammeter is used to measure current, voltmeter is used to measure voltage. In the similar way, Hall probe is used to measure magnetic field strength. Well, it consists of three things. One is a semiconductor chip, which is like shown over there. A, B, C, D is its front face. And then there's a voltmeter, and an ammeter is there. And then there is a circuit containing battery and wires. So this is the battery, switch, and connecting wires are there. So the face ABCD, which is the plane face, the bigger face, and the face behind it is exposed to the magnetic field perpendicularly, like the magnetic field strength that you have to measure, you have to expose this face over there. Well, the other two pair of faces are connected with voltmeter and ammeter. You can see that voltmeter is connected between two faces, and then the circuit is connected between these two faces as well. So all the six faces are basically like four faces are covered with wires, and then remaining two faces will be exposed to the magnetic field, which you have to measure. Okay, now moving on to its working, how it will work, how we will use Hall probe to measure the magnetic field strength. Well, let's say this is the Hall probe, which is placed over there. You can have a look on this. Well, this one is the semiconductor chip, and its faces are there, like marked as 1 and 2. Voltmeter is connected between 1 and 2. And then this is phase 3 and the phase 4, and a millivoltmeter, a milliammeter, and a circuit battery is connected with these faces. So when there is no magnetic field, then of course the current or charges will move straight through the strip, like from phase 3 to phase 4, and milliammeter will show you the constant reading. Millivoltmeter in this case will not show you any reading, as there is no potential difference across the phases 1 and 2. So it means that the current that will be moving from here, that current will be straight moving towards the other wire and moving in the green wire, and milliammeter will showing you the reading, and phase 2 will have no charge, phase 1 will have no charge. That's why the millivoltmeter will show you no reading when there is no magnetic field. Okay, now we have to move to the next situation when you place Hall probe inside the field. So let's say the same Hall probe is placed in a field, is exposed in a field such that the field lines are cutting through the Hall probe, like it's going into the Hall probe. So now we will see something happening over here, like the millivoltmeter is connected between phase 1 and 2. So what will happen then? Like you have to measure this magnetic field strength. So when the Hall probe is placed inside a magnetic field, the movement of the charges inside the strip will be affected, because like you can see that when the charges are leaving from here, like the positive charges, so when the positive charge is going to move through the Hall probe, then it will experience a magnetic field, and hence it will be deflected, like a magnetic force will be acting on it. So the charges will start to deflect either towards phase 1 or 2, right? So this charge will either deflect towards phase 1 or phase 2. Which charge I am talking about? This charge which I have drawn, it is positive, and it is entering from phase 3. It is going through the strip. It has to go to phase 4, but as it will be moving through magnetic fields, so using Fleming's left-hand rule, you can apply Fleming's left-hand rule. A magnetic force, a downward magnetic force will be acting on this charge, and it will take this positive charge over here. Like I am denoting positive charge with P because there are other crosses as well. So you might not confused with these positive, with these signs. So P for positive, it means all the positive charges will be gathering on this face. And as a result, all the electrons will start gathering over there. It's like a capacitor, like the protons going one way and the electrons going other way. And why this is happening? This is happening because when the charge is passing through a magnetic field, it will experience a perpendicular force and it cannot continue straight. It has to deflect its direction, and the protons will be moving towards phase 2 and electrons will be moving towards phase 1. How we figured that out? Using Fleming's left-hand rule. Okay, so now let's go through. As a result, the milliammeter will stop showing you the reading. Now the milliammeter will not show you any reading because the charges which are entering in the strip from 3 are not leaving from phase 4. They are actually deviating to phases 1 and 2. But the millivoltmeter will start showing you some reading, and that reading will be increasing because as the charge will start building up on phases 1 and 2, the voltmeter reading keeps on increasing. Okay, eventually the millivoltmeter reading will become stable. Like the millivoltmeter reading will start increasing from 0 to a maximum value, and at maximum value it will stop. And at that time, milliammeter will start showing you the reading. So how this has happened, let me tell you in the next diagram. Okay, so electric field setup in Hall probe. Well, how it is happening? Due to the charge separation between the phases 1 and 2, like the phases 1 and 2, phase 1 is having all the positive charge, phase 2 is having all the negative charge, there would be electric field setup inside this Hall probe, right? So this will produce electric field, and this electric field will exert a force on further moving charges in a direction opposite to the magnetic force. So let me tell you one thing. Let's say there is a positive charge coming from this wire and it has to intend to go to other, but a magnetic force is acting this way. But as electric field is also set up, so the electric field will exert a force on this charge in opposite direction. So now this charge is experiencing two forces, one magnetic force and one electric force. So if these two forces are equal to each other, then of course this charge will not go either way, but it will straight move out and it will go into the circuit. And at that time, this milliammeter will start showing you the reading again. That's what I've written over there. Okay, now at one point when the magnetic force and electric force will be equal, as I told you in the previous diagram, over here, as on this chart, the electric and magnetic force are equal, then what would happen? Well, when these are equal, you know that magnetic force is BQV and electric force is QE, right? Where Q is charge and E is electric field strength. Furthermore, this E is equivalent to V over D, where V is the potential difference between the phases and D is the separation between the phases. This is from AS electric field. Okay, now you have to insert the values. For magnetic force, you insert BQV, and for electric force, you inserted QE, and at place of E, you have written V over D. So now this Q is going to be cancelled away. So this Q will be cancelled away, and the remaining thing will be BV equal VH over D. I have written VH because it is the Hall voltage. It is named as Hall voltage. So from here, the Hall voltage will be equal to BVV. where B is the magnetic field strength which you have to measure, V is the speed of the charges inside the strip, and D is the distance between the voltmeter faces, or it is actually the length of the Hall probe. Well, this V is the speed of the charge. It is a problem for us because we don't know that with what speed the charges are moving through the Hall probe. So we have to replace this speed with something that we know. So we know from the our AS topic, electricity, the drift speed. The drift speed expression is NAVQ, where N is the number charge density, like number of charges per unit volume. A is cross-sectional area, V is drift speed, and Q is the charge. So from here, we can make drift speed as the subject as I over NAQ, and we replace it with its value in the Hall voltage. So VH was VVD, we replace V with its value, and then comes A. Well, for this strip, if you look, D is the length and T is the thickness, so its cross-sectional area, this cross-sectional area is D into T. So we replace this A with D into T. This D and D will be cancelled away. So our new expression is Hall voltage equals BI over NTQ, right? So this is actually the expression that we have required. Furthermore, we can make B as the subject as we have to find B, which is magnetic field strength. So you can just make B as the subject. So it is NVHQT over I, where N is the number charge density, it is material feature, VH is the Hall voltage, you will measure it through voltmeter, Q is the charge, which is elementary charge, 1.6 in 10 to the minus 19, T is the thickness, which you will measure from here, and I is the current, which you will measure through ammeter, right? So it means that you only have to measure two things from here, like you have to measure Hall voltage through voltmeter, you have to measure this current through ammeter, that's it. This T is the thickness, which you will measure with ruler or vernier calipers. Q you already know, elementary charge, and N you already know, which will be the feature of the material. Okay, the last thing from it is, as you know, that Hall voltage is BI over NTQ, so we have to look for the factors of the Hall voltage. So from the equation, there are several factors. One of them is magnetic field, V proportional to B. If greater magnetic field, then greater Hall voltage will be displayed by the voltmeter. The next one is N, where N is the number charge density. For conductors, N is very high because conductors have a lot of free charges. So N would be high. For semiconductors, N would be low, right? Because in N, there are less charges. But as the expression shows that Hall voltage is inversely proportional to N. So it means that if you use semiconductor, its low value of N will make sure that there would be greater Hall voltage. So that's why we prefer to use semiconductors over the conductors. This is important past paper question as well. They'll ask you that why we choose semiconductor chip instead of conductor chip in the Hall probe. So we'll say that as in the semiconductor, the charge carriers are less as compared to conductor. That's why the Hall voltage value would be higher, and we can easily measure that. The last thing is the thickness of the strip. If you use thin strip, so it will give you more value of the Hall voltage. Okay, that's it, students. Thank you so much for today. I hope that things make sense for you. If in case you found anything troublemaking, you can talk about that in the comments below. Our next video will be about the qualitative and quantitative analysis of fields, like qualitative and quantitative analysis of fields. Until then, goodbye.